So far we've been looking at simple harmonic motion only in terms of the forces, but of course we can also study this system in terms of the energy. An oscillating system has energy, and this energy is in two forms: kinetic energy and potential energy. For a mass on a spring, the kinetic energy equals a half mv squared, and the potential energy, E potential, equals a half kx squared. The kinetic energy can be thought of moving energy, and the potential energy as the stored energy of the system. Remember, m is the mass in kilograms, v velocity meters per second, k spring constant newtons per meter, and x is the extension of the spring. Again, this is a mass on a spring, the classic oscillating system. Later on in this video, I'll talk a little bit about the energy considerations for a pendulum, where gravity drives the restoring force. The physics in these two cases is the same. Let's talk now about the potential energy of an oscillator. Remember that potential energy is the ability of a system to do work. Example, again, a mass on a spring. The spring does work by exerting a restoring force, which is equal to minus k, the spring constant, x, the extension. The work of this system can be seen visually if we plot the force versus the extension. It can be seen below. The gradient of this line is k, and that is the spring constants of the system. The area under this curve is equal to the work of the system, which is of course an energy and measured in joules. You'll remember from mechanics that work, W, equals force times extension. So it's the product of the force and the distance over which the force is applied. Again, let's plot our little force versus extension diagram here, and we can see that the work equals the area under the curve. So if we take this top equation here, we can see that work must equal a half, because we've got a triangle, Fx. Now we know that F equals minus Kx, so we can sub that into the equation, and we see that now work equals a half Kx times x, which equals a half Kx squared. This is where the equation, the energy potential equals a half Kx squared, comes from for a mass on a spring. So let's look at the total energy in a simple harmonic oscillator. In a perfect simple harmonic oscillator, which is the systems that we've been thinking about and examining so far, there are no dissipative forces, i.e. the system would go back and forth forever. This is obviously not true in real life, and we'll get to that in the next video, where there are damping forces that take energy from the system. Examples of a damping force would be friction or air drag. However, in a perfect simple harmonic oscillator, the total energy of the system is conserved. This means that kinetic energy and potential energy are constantly being transferred between the two. So a half mv squared, the kinetic energy, plus a half kx squared, the potential energy, has to equal a constant. This general principle of conservation of energy is true for all simple harmonic oscillators, including examples like the pendulum, where gravity drives the restoring force. To get the equations for a pendulum, we replace the velocity by L omega, k by mg on L, and x by L theta. If we sub these into the equation above, we have a half ml squared omega squared plus a half mg L theta squared equals a constant.